In this lesson, we're going to continue our exploration of inverse functions. We're going to continue looking at how to tell if something is a function and whether or not its inverse is a function. We will determine how to figure out whether or not two functions are inverses of each other, and we will talk about how to restrict the domain of a function so that its inverse is a function. So recall that we said if a function is one-to-one, then it's going to have an inverse function. And so in order for a function to be one-to-one, what would need to be true is that every x value maps to exactly one y value, and there are no repeated y values. So if we look at this first example, it says, given the relation below, find its inverse. Is the relation a function? Is the inverse a function? So if we look at this, first off, to determine if it is a function, we would look at the x values. We have 0, 2, 3, and 4. And so our first question would be, do each of these x values map to exactly one y value? The answer to that is yes. So this relation is a function because each x value maps to one y value. The second question is this function one-to-one? So this function is one-to-one because if you look at the y values, you have -1, 0, 2, and 3. There are no repeated y values, so that would tell us that this function, or this function, since we just said it is a function, is one-to-one. And because this is a one-to-one function, then we know that this inverse is going to be a function. So the inverse will be a function, which means that it will pass the vertical line test. And if we wanted to find the inverse of this function, what we would do is we would just switch the x and y values. So we'd have a point -1, 0. We'd have the point 0, 2. We'd have the point 2, 3. And we'd have the point 3, 4. And so that would be our inverse function for this, for the original function. Now, the next question says to find the inverse of y equals x squared. Is the inverse a function? Is y one-to-one? So if we look at this, let's just answer these first two questions first. Is the inverse a function? And so if you think about what this graph looks like, this is going to be a parabola that has shifted down 1. So it's going to look something like that. And so if we think about what this, does this pass the horizontal line test, the answer to that would be no, it does not, because if we draw in a horizontal line, we see that the horizontal line will pass through the graph of y equals x squared minus 1 twice. So what that tells us is that the inverse is not a function. Okay, the y is a function, but it's not a function, and that's because it's not one-to-one. It does not pass the horizontal line test. And so we know that it's not going to, the inverse will not be a function, but we can still find the inverse. So to find the inverse, we'd have to switch our x and y values, and we'd have x plus 1, and then equals y squared. And then we take the square root of both sides, and that would give us plus or minus the square root of x plus 1 equals y. And so if we were to graph that, what we would have is we would have a square root function, one the positive side and the negative side. And so you can see that this is not going to pass the vertical line test, so it's not a function. So in order to figure out whether or not two functions are functions are inverses of each other, what we want to do is we want to look at the compositions of the two functions. Because if we take f inverse of f of x, it should equal x if the two functions are inverses of each other. And if you take it the other way, f of f inverse should also equal x. again, remember another way to write this is f inverse of f of x should equal x, and f of f inverse of x equals x. And so again, what this means is if you are plugging in your original function into your inverse, you should get x out. If you're plugging your inverse into your original function, you should get x out. And so let's take look at two examples here. So you'd have f of x is equal to 2x minus 7, g of x is equal to x plus 7 divided by 2. The question is, are these two functions inverses of each other? And so if we look at this, we would have, we need to find out if f of g of x, does that equal x? And so we would have to take 2, and then we would plug x plus 7 in for x. So in parentheses, x plus 7 divided by 2 minus 7. The 2's cancel. You have x plus 7 minus 7. 7 minus 7 is 0. So f of g of x is equal to x. Now that doesn't necessarily mean that they're inverses yet. We do and should check the other way. So is g of f of x also equal to x? So you'd have, you have to plug in this case, you're plugging 2x minus 7 in for x. So we'd have 2x minus 7 plus 7 divided by 2. Negative 7 plus 7 is 0. So you have 2x over 2, which is just equal to x. And so again, because f of g of x and g of f of x both equal x, we know that these two functions are inverses of each other. So f and g are inverses. If we got something besides x for either one of those, then we would say that it is not, that they are not inverses of each other. So let's take a look at this one. Again, we would need to check f of g of x. That would be 3 times 1/3 x minus 4 plus 12. If we distribute that, we'd have x minus 12 plus 12. Those cancel, you're left with x. Then you'd have to check g of f of x. So we'd have 1/3 times 3x plus 12 minus 4. You distribute that, you get x plus 4 minus 4. That's equal to x as well. And so we would know f and g are inverses. Again, if you got anything that was not equal to x, then you would know that they are not inverses of each other. So this next question says, graph the inverse for the relation shown. Is the inverse a function? So we can answer this question right now. The answer to that is no, because we'll call that f of x does not pass the horizontal line test. Again, the horizontal line test is if we draw a horizontal line and we see that there is at least one y value that maps the two x values, or that have two x values mapping to it, then we know that it is not a function, or that the inverse will not be a function. So does not pass the horizontal line test, well, the inverse will not be a function. So then to figure out what our graph is going to look like, I would recommend that you make a table for some key points that are on the original graph. So if we look at this, we have 0, -1, we have 1, 0, and we have 2, 3, and then we would have -1, 0, and -2, 3. And so if we go ahead and take these xy points and we flip them to make our inverse. So remember, when we are finding our inverse, we exchange our x and y values for each other. So we'd have 3, -2, 0, -1, -1, 0, 0, 1, and 3, 2. And we put those points on the graph. So 3, -2, 0, -1, -1, 0, 0, 1, and 3, 2. And so what we have here is we have this graph. It looks like this. So it looks like a sideways parabola, like so. And remember, when we have our inverse graph, really what it is a reflection over the line y equals x. So if we look at that line right there in red, we are reflecting the black graph over the green graph, or over the red line. So you can see this section right here is reflecting over to there. This section up here is reflecting over to here. So they're reflecting over the line y equals x. Okay, so when the inverse of a function when the inverse of a function f is not a function, one thing that you can do is you can restrict the domain of the original function so that the inverse is a function. So if we look at example 4 again, for example 5, if we look up here at this original example in example 4, we had a parabola that is x squared minus 1. And the question is, how could we restrict the domain of the given function to create an inverse that is a function? So what we would need to do is we would need to restrict our domain such that the black graph would pass the horizontal line test. And so one way that we could do that is if we took that and we only considered the right half of our graph. So if we only looked at this piece right here, then that would pass the horizontal line test. Or if we only looked at this piece right here, it would pass the horizontal line test. So one way that we could restrict the domain is we could say that we had the equation y equals x squared minus 1, but we're going to restrict the domain to be 0 to infinity. Or we could restrict the domain to be negative infinity to 0. So you can restrict it so that you only have half of the original function. And again, you can do that anytime that you have a function that is not one-to-one. You can find a way to restrict that domain so that you can have an inverse that is a function. And then last few examples here, it says given the function f of x equals the square root of 2x minus 1 plus 3, it says find a domain and range for f of x. So if we look at this, we can find out that our domain here, if we consider this graph, so we know that this function is going to be, had moved right 1 and up 3, and then it will look something like this. And so our domain would be positive 1 to infinity, and our range would be equal to 3 to infinity. And so it says find the inverse of this function, f of x. So again, to find the inverse, we would take this and say, let's flip our x and y values. So we'd have the square root of 2y minus 1 plus 3. That would give us x minus 3 equals the square root of 2y minus 1. We'd square both sides, and that would give us x minus 3 squared is equal to 2y minus 1. We would add 1 to both sides, and we'd get x minus 3 squared plus 1 equals 2y. And finally, we would have y is equal to x minus 3 squared plus 1 all divided by 2. And so that would be our inverse function. And so, again, we know that the inverse is a function because f of x passes the horizontal line test. And then it says determine the domain and range of the inverse. So remember, when we are finding the inverse of a function, we are just switching the x and y values. So that means that the range and the domain flip for our inverse, which tells us that the domain of our inverse is going to just be our range from our function, and then our range of our inverse is just going to be the domain of our function. And it says sketch the graph of f of x and its inverse. So we know that we're going to have a parabola that's going to have, we're only going to have half of a parabola, and it's going to go from 3, have its vertex at 3, 1, and then it's going to look something like that. So it's reflected over the line y equals x. So if we were to draw that in so you could see, it kind of would look like that. All right. And then looking at a few more examples of the functions 9x squared and the square root of x divided by 3 inverses of each other, use compositions to explain. So you'd find f of g of x first. So you'd be plugging g into f, so you'd have 9 square root x over 3 squared. And that would give you 9x over 9, which would be equal to just x. And then you'd find g of f of x. And so you'd have the square root of 9x squared over 3. The square root of 9x squared is going to be 3x over 3, which is equal to x. So they are inverses of each other. Now, looking at these problems, we are using the table and graph provided of f of x and g of x to find out the value of the inverse functions. So in this first example, it says f inverse of -4. So if I want to find out what f inverse of -4 is, I have to remember what the relationship is between f inverse and f. So if the x value of f inverse is -4, that means that this was the same as when f of x equals 4. So, or f of x equals -4. So, because again, remember you're switching the x and y values. So since -4 is the x value of f inverse, that means it was the y value of f of x. So if we look at f of x and find where y is -4, you would find out that f inverse would be equal to 6. If you look at f of x, and again, f inverse of -9 is saying, when was f of x equal to 9? Well, you find right here, that would be -4. F inverse of -10, again, we're asking when was f of x equal to -10, right there. So f inverse of -10 is going to be 8, because you flip the x and y's. If we want to know f inverse of 5, again, we want to know when was f of x equal to 5? It was when x was 3, so we flip the x and y values, and we find that we have that is equal to 3. And you can do the same thing with g of x. When you have a graph, it says g inverse of 5. So again, if this is g, this means I want to know what was the x value when g of x was 5. So there we go, there's 5. So that would be 3. So g inverse of 5 is equal to 3. G inverse of 0 means what was the value of x when g of x was 0. So we come over here, g of x was 0 at x equals 2. So we'd have that equal to 2. What was the value of g of x, or what was the value of x to make g of x -3? That would be right here at 1. So we'd have this is equal to 1. And then finally, this would be what is the value of x to make g of x equal to -5? -5, that does not exist. So does not exist. Okay, because g of x never reaches a y value of -5. Here we have f of x equals 3 over 2x minus 1. Find f inverse of 4. So in this case, I would just want to, there's a couple ways you could do this. F inverse of 4, I could just find f inverse. So I could switch the x and the y like so, and then solve x plus 1 times 2/3 equals y, and then plug that in. So f inverse of 4 would be equal to 2/3 times 4 plus 1, which would be 2/3 times 5, or 10/3. Or I could also just say simply, again, f inverse of 4 would be the same as saying, okay, what x value made f of x equal to 4? So you could say 3 over 2 x minus 1 equals 4. Add 1, 3 over 2x equals 5. Multiply by 2/3 on both sides. That gives you x equals 10/3. Same answer both times. And finally, the last question, the graph of a polynomial function passes through the points -1, 1, 0, 4, and 2, 3. Can its inverse be a function? Think carefully about this. If we plot these points on the graph or on a coordinate grid, we would have -1, 1 would be somewhere right there. We'd have 0, 4, which would be right here. And then we'd have 2, 3, which would be right here. And so if this is a polynomial function, we know that it would be continuous. So it goes something like this. We don't know what it does after that. It does something. It could go like that. It could go up like that. But what we do know is that because the polynomial had to go through y equals 3 in order to get from y equals 1 to y equals 4, we know that there are two x values that map to 3. Therefore, this function is not 1-to-1. So the inverse is not a function. So go ahead and begin looking at the homework. If you have any questions, come to class tomorrow and make sure you ask them.